Really
Yes, sir.
Yes, sir.
Okay.
Yes.
And you can see this. I think I have to do it this way only. No. You can see the screen.
Yes, sir.
Okay. Okay, so I think we should start. It's nearly time. 1 minute early. It doesn't matter. So do you have any questions from what we have done last time? Are there any difficulties that you may have had in reading the notes, or any other questions that sort of came up? So, I mean, last time I was just doing what I was saying. There exist biholomorphic maps between two regions, okay? And the regions are, in some sense, the most important regions that you will come across. They are upper half planes, or they are quadrants, or they are upper half disks, or they are sectors, okay? So in some sense, these are the most natural domains that one thinks about. Of course, you can have more complicated domains. And one of the theorems is that really those complicated domains are not more complicated than these domains, okay? And that is a Riemann mapping theorem. So I'm not sure if I will do that. So we'll see. If one is energetic enough, one can do that. It's not that much out of the grasp, but it does involve some little bit of work and a few more ideas. So let's see how that goes. I've had this other comment that I probably am going a bit too fast, and people are finding it a bit difficult to understand or keep up or whatever it is. And I've heard a comment that the last lecture was not that fast, therefore it was better. So if you feel that I am going a bit too fast, please do tell me. I mean, the idea here is not to cover some syllabus per se, but the idea is to hopefully make you think in a slightly different manner than what you have been used to. Or idea also is to sort of point out some things that are important, which you may not have initially thought are important. Okay, so it's not that I have to finish it's not that I have to finish, quote unquote, a syllabus as such, but there are a lot of ideas that are involved here. And again, they're very basic ideas, but it takes some little bit of time to understand that these ideas are important. Okay, so if you have any difficulties, you please do ask me to slow down or repeat myself or something like that. And again, the point is that I had said this earlier, I'm saying this again, that you will be able to understand what is going on only after you write it out once in longhand. Don't even type. Okay, I don't mean LaTeX business. Before you do the LaTeX business, you must understand what is going on. And the only way you will understand what is going on is by writing it out with pen and paper. Okay, writing it out, everything out yourself. Because only when you write it out do you have some appreciation or idea of why certain words were used. Okay, and writing is an active undertaking. Reading is somehow a passive undertaking, which it should not be, but most people, when they read, they don't question every line. When you write it out, you're more likely to question every line. Okay, so when you write everything out, you please question why something was written in this way, okay, at every stage. And then you will be able to appreciate this. I'm repeating myself. I know I'm repeating myself, but I mean, some of you had sort of said that this is going a bit too fast. You don't understand what's going on. And the only way of understanding this is by writing it out yourself. And there's one more comment that I should make here is that, you know, this is probably the second time that most of you are seeing most of this content, okay, material. Because you would have seen this in your MSc classes. I'm not doing anything very different from what is done in most MSc classes. So you would have seen it there, okay, and this should be the second time when you're seeing it, okay. There's also a problem that usually the complex analysis course is not really taught quite that rigorously or fully in the MSc course, okay. That's unfortunate, but that is a case which is true. So some of you may some of you may be reading these things for the first time, okay? And the general comment will be that, you know, you have to read the same thing over and over again, same subject matter over and over again, or hear the same subject matter over and over again. So I say this all the time. Some of you have heard this before. The first time you hear something, usually you don't understand it at all. The second time you hear something and write it out, you understand it better. The third time you hear something, the same subject, the third time you hear something and write it out, okay, it gets even clearer. And the fourth time you hear the same subject and write it out, by the fourth time you do this, you'll say, all this is obvious. Why is a person wasting my time? Okay, so you have to come to this fourth time of reading, or fourth reading and writing of the same subject. Only then will you understand exactly what is going on, because by that time you would have known you have done this thing 3 times already. So this, of course, is applicable to whichever subject you're studying, okay? And please remember that you have to read this over and over again, 3 times at least, to sort of become a bit more familiar with whatever is going on. So even after this AFS-I is over, I hope you will spend time reading these things and writing these things out over and over again, and only then will you begin to understand what is going on. Okay, so there are no questions or difficulties as I understand it. Is that correct? Does anyone have any questions, difficulties about whatever I have done so far? No, so I should continue speaking. Okay. So where were we last time? Okay, last time I had before this. Why is that not opening? So before this, as I said, I was drawing various pictures of what goes to what, okay, which region goes to which region. For example, Fz equal to e to the iz maps a half strip, okay, to the half disk, and so on and so forth. And z plus 1 by z maps something to something, okay. And also this business about, I had some quarter plane, upper half disk to quarter plane, the quadrant. And I mean, to verify that this is a biholomorphic map which maps this to that, okay, you have to sit down and look at a point in the upper half disk and show that it has both real part and imaginary part greater than 0, that kind of thing, okay, which is not particularly difficult to do. And it's good to sort of go through these calculations. Okay, I've sort of given you the outline of these calculations, but it is good to sort of sit down and do these by hand yourself, as I said over and over again. Okay, and also the point is that you know that as far as the quadrant goes, the axis, okay, is not in the quadrant. It's supposed to be the open quadrant. This on the left-hand side is the open disk, is mapped to the open quadrant. Okay, and again, you should sort of try to think about pictorially, okay, what happens to, you know, lines, what happens to circles which are inside this this disk, where do they go in the quadrant, okay? And also you should try to understand what happens to the boundaries. You see, all these functions have continuous extensions to the boundary. The functions are holomorphic, but the continuous extension, okay, is not holomorphic. You cannot extend it holomorphically to a larger region. Okay, you can extend it continuously to the larger region, and you will understand that the boundary behavior of holomorphic functions can get very complicated. Okay, I mean, if you have this quadrant, there is no way that you can straighten out this quadrant, okay, by even a differentiable function, a real valued differentiable function from R2 to R2. Okay, whereas you can map the interior to the unit circle in a very nice manner, in a holomorphic manner. So this business about boundary behavior of holomorphic functions actually is something that is very interesting and also quite difficult to understand in most cases. Okay, and you will understand that even this boundary behavior, okay, arises actually physically. Okay, when you're talking about streamlines and how do you go around streamlines and what happens to the boundary. So people who do hydromechanics or aerodynamics or something like that are worried about these kind of questions. Okay, I'm sure if you have any friends doing PhDs in aerodynamics or fluid flow or any of that kind of thing, they're very interested in the boundary behavior of these holomorphic functions that we get. I hope you will find out something about it. So anyway, I had done various cases and then talked about various, you know, sin Z. Finally, I stopped with sin Z, I said. Sin Z is something like this. It's a composition of so many functions, and you're mapping various things to various things, okay? And you get the upper half plane, okay? And each of those components are holomorphic and therefore the biholomorphic, and therefore the composition is biholomorphic, okay? And where does the boundary behavior go from? You must understand this boundary behavior, what happens, okay? So there's lots of things to be understood, even though I'm sort of telling you what the behavior is. You have to understand that this is actually the behavior. So there's some things that have to be proved or seen or verified, okay, in this picture. Fz equal to sin z goes from minus infinity to minus 1 as the point goes from minus pi by 2 to pi by 2, okay, along the real line, and it goes from 1 to plus 1, etc., etc. These kind of things you must be able to understand. And finally, I had come to the Schwartz lemma, which I had covered last time, but it's good to do it again. Okay. So another psychological statement that you will realize is that when you're teaching something, it's always good to repeat yourself, because there will be some in the class who will say that, this was repeating yourself. Yes, but most of the people would have forgotten what was done in the previous class by the time the next lecture starts. So this is, you're either in one of these two categories. You remember that I had done this last time, and then why is this person doing it again? Or you're in the category where, was this done last time? I don't really know. Okay. Anyway, So what is the Schwartz lemma? You take a function from the disk to the disk, which is holomorphic, which maps 0 to 0. So if it maps 0 to 0, then fz is less than equal to mod z for all z in D. I'm given that it maps D to D. Okay. If for some z naught, fz naught is equal to z naught, okay, then f is a rotation. If f is a rotation, then definitely for some z naught, fz naught is equal to z naught, namely the point z naught equal to 0. And f prime 0 is less than equal to 1. If f prime 0 is equal to 1, then f is a rotation. Why? I mean, so this is what we want to prove. So f is a rotation means that fz is equal to e raised to I theta z for some fixed theta. So I've called it theta naught. So why f is holomorphic? It has a power series expansion. F0 is equal to 0 means A0 is equal to 0. That means Fz divided by Z is A1 Z to the 0 plus A2 Z to the 1 plus so on. This is a power series that will converge, and therefore Gz over Z, Gz, which is Fz divided by Z, okay, has a removable singularity, and therefore you can remove that singularity, okay, and you get some analytic function. Gz is an analytic function. For each mod z equal to r, which is less than 1, Gz, okay, which is fz by z, is less than 1 over r, okay? And therefore, this is what for mod z equal to r. So you look at this region mod z equal to r, and you suppose that r is greater than half, okay? I'm interested in what happens when r tends to 1. I'm not interested in what happens as r tends to 0, okay? Even when r tends to 0, okay, Gz is going to be bounded, but that is not what I'm interested in. So you take r greater than half, okay? Gz is less than 1 by r for mod z equal to r, and therefore Gz is 1 by the maximum modulus theorem. Gz is less than 1 by r, less than or equal to, I should say that. For all z, it should be strictly less than. For all z with mod z, strictly less than r. And therefore, letting r tend to 1, we get Gz is less than 1 by r for all r less than 1, and therefore Gz is less than or equal to 1 for all z less than 1. Okay? Less than 1 is the z in D. So Gz is less than 1 for all z in mod z less than 1. That means fz is less than mod z. This is the first thing you want to prove. And if fz is equal to fz naught, then Gz attains its maximum for some z naught in the unit disk. Gz attains its maximum at an interior point, okay? And therefore Gz is constant, and it's a constant of absolute value 1. Therefore Gz is e raised to I theta naught, and therefore fz is e raised to I theta naught z, okay? And why is it not going up and down? Oh, this is the end of this page. And the third part of it is that what is f prime 0 is limit fz minus f0 over z. F0 is 0, so it is fz over z, which is g0. That means f prime 0 is g0, okay, which is less than or equal to 1. And f prime 0 equal to 1 means that g0 has its maximum, and therefore it's a constant. So I'm using the same thing over and over again. This is a consequence of the maximum modulus theorem, okay? So this is your, as I say, usually this is your plain, simple Schwartz lemma. Now there are more and more sophisticated versions of the Schwartz lemma. They are given in Stein and Shakarchi, and they're used in different ways. And I mean, I hope you will look at those exercises which sort of tell you a souped up version of Schwartz lemma. Just a moment, I'll be back in a moment. Hello? Hey, Jen. Hello. Hey, Jen, I'm in the middle of a lecture. I'm calling you. Okay, yeah. Okay, so there are more and more souped up versions of Schwartz lemma. There are some of them are quite important, and they're given in this book, Stein and Chakarchi. Please have a look at those, and you will understand that even these souped up versions are not fundamentally different from this Schwartz lemma that we have done right now. So again, the first thing you use is the plain, simple, vanilla Schwartz lemma, and then you can get more and more complicated flavors out of it. Okay, so please have a look at some of these other versions and slightly more complicated versions of Schwartz lemma. Okay, so we are going to use the Schwartz lemma in something. So the question, someone had asked me this question last time, that what are all the automorphisms of the disk? What is the meaning of automorphisms? We want a holomorphic function from D onto D into a bijective map from D to D that is holomorphic and whose inverse is also holomorphic. Okay, and we already know that this is a consequence of the open mapping theorem also, that if you have a bijection and it's holomorphic, then it is open, and then the inverse map is continuous you get, but then you will also get that the inverse map is holomorphic. Okay, so we know that this rotation by theta, okay, is a map from D to D, and it is holomorphic, and rotation by theta, okay, has an inverse, that is rotation by minus theta. Okay, so R theta has a holomorphic inverse, and this is the meaning that R theta is a holomorphic automorphism of D. In this setup, when we talk about an automorphism, okay, the automorphism is always supposed to be holomorphic. The map is holomorphic and the inverse is holomorphic. Okay. So, I mean, again, you can say something about this is there's a category that is going on here. So what is the objects, etc., etc. There are versions you can say these things. So R theta is holomorphic bijective. R theta inverse is R of minus theta, which is holomorphic. And the question we want to ask is, what are all the holomorphic automorphisms of D? Okay. So what are all the holomorphic automorphisms of D? So what is the lemma? If alpha is in C, mod alpha less than 1, then psi alpha of Z, which is alpha minus Z over 1 minus alpha bar Z. So this is a particular case of a Mobius transformation. Okay, AZ plus B over CZ plus D. And you can figure out what the A is. A is 1, A is minus 1. Okay, AZ plus B, B is alpha. Okay, CZ plus D, C is minus alpha bar and D is 1. Okay, so this is a particular case of the Mobius transformations, and I had sort of talked about this right in the beginning. I think it was in one of the problem sessions or one of the exercises where I had talked about this. Okay, so I'm basically doing that exercise now. So mod alpha is less than 1. The only place where you have problems with holomorphicity of this psi alpha is when 1 minus alpha bar Z is equal to 0. That means Z is equal to 1 over alpha bar, but mod alpha is less than 1. So mod alpha 1 over mod alpha bar is greater than 1. So the only place where you have a difficulty is outside the disk, and therefore this is holomorphic on the disk. Okay. Now this map has an extension to, see, the only problem I have is when mod alpha is greater than 1. Therefore, on Z, mod Z equal to 1, okay, I can still define this. Okay, and it's, so the point is that this psi alpha of Z is holomorphic on the interior, the disk, okay, that is the interior of the disk, okay, and it has a holomorphic extension to a slightly larger set. How large depends on alpha. Okay, there exists an open set which contains the unit disk on which psi alpha is holomorphic. Okay, because the problem arises at 1 over alpha bar, which has absolute value strictly greater than delta greater than 1. Okay, so psi alpha in fact has a holomorphic extension on a slightly larger disk. How large that disk extension is depends on the alpha. Okay, so if mod alpha less than 1, psi alpha is holomorphic on D, and if mod z is equal to 1, I can still define psi alpha, okay, this quantity, and psi alpha of z, z is equal to e to the I theta, okay, so this is alpha minus e to the I theta into 1 minus e to the minus I theta z. Pull out the e to the I theta out. Sorry, you're supposed to pull out e raised to minus I theta. So there's a misprint here. You pull out e to the minus I theta, so you get e to the I theta minus z here. And therefore this quantity has absolute value 1. Okay, this over its conjugate. I made some, so what should I write here? Alpha 1 minus alpha bar z. Okay, so z I'm putting as e raised to I theta, e raised to, I made some mistake here. What should I put here? Why is the alpha and a some alpha bar? There's some writing mistake here. Okay, so I should get alpha minus e raised to I theta and alpha bar e raised to I theta minus alpha bar here. So I've made some goof up here. So please correct it. Okay. What do I want to do? Alpha is there. So there should be an alpha instead of a z. This z should be an alpha. This z should be an alpha. Okay, that's a mistake I've made. Okay. So anyway, this has absolute value 1. And therefore, if mod alpha less than 1, this has absolute value 1. So therefore, the unit circle is mapped to the unit circle, okay, by psi alpha. And therefore, by the maximum modulus theorem, psi alpha z must be less than 1 for all z in D because it is non-constant. And psi of alpha is equal to 0. Again, just wait a moment. I'll be back in a moment. Okay, so sorry about that. As usual, some interruption. So anyway, so this z should be an alpha there, and therefore you get this as absolute value 1, and psi of alpha is equal to 0, which is in D. Okay, you see, you have to say this because you're not sure what gets mapped to what, and I want to say that D gets mapped to D. It's not that D gets mapped to something outside D when I want to use the maximum modulus theorem, and therefore you get psi alpha of z is less than 1 for all z in D. Therefore psi alpha maps D to D. Okay. So the exercise is that psi alpha composed with psi alpha is the identity. Okay. So please do this. We have to plug in psi alpha in psi alpha of z in psi alpha, and see that you get z. And therefore the inverse is psi alpha itself. Okay, and therefore you have that the inverse exists with maps D to D and it is holomorphic, and therefore psi alpha is an automorphism of D. Okay, and psi alpha of 0 is equal to alpha and psi alpha of alpha is equal to 0. That means psi alpha interchanges 0 and alpha. Okay, so what do we want to prove? We want to prove that every automorphism of the disk is a psi alpha up to a rotation. Okay, so what have I done up to now? I've said that psi alpha is an automorphism of the disk and the rotation is an automorphism of the disk. Therefore, the composition of these two things is an automorphism of the disk. And what we're doing here is the converse, that every automorphism of the disk is of the kind psi alpha together with some rotation. Okay? Why? So you have an automorphism and therefore there exists an alpha for which f of alpha is equal to 0. It must be bijective. Okay, 0 is in the image. There exists an alpha such that f of alpha is 0. Take G equal to f composed with psi alpha. Okay, psi alpha is an automorphism, f is an automorphism. The composition is an automorphism, and this evaluated at 0, psi alpha of 0 is alpha, f of alpha is 0, so G of 0 is 0, and G maps D to D. Okay, and therefore G of Z is less than Z for all Z in D. Now G inverse is also there. Okay, now this is one place where, this is one place where this idea is also important, that you have G0 is 0, therefore G inverse, which also exists and is holomorphic, G inverse of 0 is 0. Okay, so you can apply Schwarz lemma to G inverse, which gives you that mod G inverse of W is less than or equal to mod W for all W in D. Okay, now I'll put W equal to G of Z. So if W is equal to G of Z, it says mod Z is less than or equal to mod G of Z. So we have these two inequalities. G of Z is less than or equal to mod Z, and mod Z is less than or equal to G of Z for all Z. And therefore you get by Schwarz lemma, Gz is equal to mod Z, and again by Schwarz lemma, you must get that G of Z is equal to e raised to I theta times Z. Okay. G of Z by Z is a constant, and that constant is absolute value 1. So it is some e raised to I theta. That means f composed with psi alpha is equal to e to the I theta Z. Okay, then you put Z equal to psi alpha of zeta. So you get f composed with psi alpha of zeta is equal to e to the I theta psi alpha of zeta. But psi alpha composed with psi alpha is identity. So you get f of zeta is like this. Okay. So every automorphism is given by a rotation followed by one of these maps. And therefore, the only automorphisms that fix the origin. Okay. So you want f of 0 equal to 0. Okay. The only automorphisms that fix the origin. So f of 0. What is f of 0? F of 0 is you're putting zeta equal to 0. Okay. And therefore, I made a mistake here. No? Psi alpha of zeta. So what I should write here is psi alpha of zeta. So there's no z here. So this again is I should have been more careful when I'm writing this down. There's no z here, there should be a alpha. So anyway, please, you should be able to. This is the kind of thing that when you write out, you will understand that there are mistakes in this. Okay, and you have to sit down and correct the mistakes. So in this line, there should be no z. There should only be an alpha. So the only automorphisms from D to D that fix the origin are the rotations. You know that the rotations fix the origin, and these are the only ones. Okay, so again, this is a consequence of Schwartz lemma. The group of automorphisms of D, okay, act transitively on D. I hope you understand that there's something that's going on here that is similar to, in fact, it is the same as what you have been doing in your algebra class. You have groups acting on sets, okay, and you're worried about the orbit of that group. In the algebra class, most of the groups that you have been talking about are finite groups, okay, and most of the sets you have been talking about on which the group acts, most of them have been finite sets, okay, in some sense. Whereas here, the group that I'm talking about, so I should have written this there, this automorphisms of the disk forms a group. You take phi1 and phi2 are automorphisms, then phi1 composed with phi2 is also an automorphism, and phi1 inverse is equal to phi1. Okay, each element has order 2. In this group, each element has order 2. Well, not quite, because you have those rotations also there. So I should not make that statement. If there is no rotation present, then each element has order 2. Okay. So in fact, you should ask questions here about normal subgroups, quotient groups, etc., etc. here. Okay. So group of automorphisms acts transitively on the disk. So as I said, this is very much in the spirit of the kind of things that you have been doing in the algebra course that is going on simultaneously. Only here, the groups are infinite groups, and the set on which they are acting are infinite sets. Okay. So the first exercise is the group of automorphisms acts transitively, because what is the meaning of acts transitively on that set? That means given any two elements in that set, you can find an element in the group which takes this point to that point. Given any alpha and beta in the disk, there exists a phi such that phi is an automorphism of D, phi is an aut D, and phi maps alpha to beta. Why? Because you can always find, given any alpha, you can find an automorphism which maps alpha to 0. Similarly, you can find an automorphism that maps beta to 0. So if you call those automorphisms phi1, mapping phi to alpha to 0, and phi2, which maps beta to 0, then phi2 inverse phi1 is going to map alpha to beta. Okay. So to show that it is transitive, any automorphism group is transitive. Okay. All you have to do is that you can map any element to a fixed element. Okay. This idea we're going to use again. So there was something I wanted to make here before I go ahead, which is a fuss at this stage. Okay. Here, G is G maps D to D, therefore GZ is less than equal to Z. But the same point is true for G inverse. And when I apply it to G inverse of W is less than equal to W, and I put W equal to GZ. When you put W equal to GZ, you get mod Z is less than GZ. Okay, so look at these two inequalities, GZ less than mod Z and mod Z less than GZ. So I can do this because G inverse satisfies the same properties as G. Okay. So this idea actually is used in quite a few places. When you have an inequality like that, Gz is less than mod z. You apply the same inequality to the inverse. If you know that the inverse satisfies the same properties that the original G satisfies, okay? And then that less than or equal to sign becomes a greater than or equal to sign, okay? And therefore you will have equality there. So this idea you will see coming up in quite a few places. Okay, at least a couple of other places you will see this idea coming up. G and G inverse satisfy the same property. So you have an inequality of G like this, then it is actually an equality. Okay. Very good. So we have the group of automorphisms, and the group of automorphism acts transitively on D. Does it act doubly transitively? Have you had this? Have you talked about this in the other class, in the algebra class? Something group acting on a set, and does it act doubly transitively? You've talked about transitively, I know. What is the meaning of doubly transitively?
No, sir, we haven't.
So what do you think it should mean? See, transitively means given any 2 points A and B, you can go from A to B by some element in the group. Doubly transitively should mean that given 4 points A1, A2 and B1, B2, okay, can you find one element which takes A1 to B1 and A2 to B2? Okay, so you're mapping a pair of points to a pair of points. And this idea also is, in some sense, it's going to arise again sometime later, but doubly transitively things are also to be worried about. Anyway, so that is not quite what we are talking about here. So you are beginning to see, as I said in the beginning also, mathematics is one subject. Algebra is not distinct from this. Analysis is not distinct from complex analysis, is not distinct from differential equations or whatever. So even though you might be doing your PhD in one particular area, does not mean that you have to ignore other areas. Of course, you must spend most of your time in that area in which you're writing a PhD thesis, but you should also be aware of things around you. Okay, so now we know what automorphisms of D look like. And the other thing we are interested in is the upper half plane. So the question is, what can you say about automorphisms of the upper half plane? I hope you understand where we are. We are at the stage where we know what every automorphism of the disk is. Okay? And the question you want to ask is that, therefore, can you write down what every automorphism of some other region is? And the first region you will think about is the upper half plane. Okay? So we have this map. So the point is that given that we know the structure of the group of automorphisms of the disk, can we say something about how the group of automorphisms of the upper half plane looks like? But we already know that there is a biholomorphic map between the upper half plane and the disk, which has an inverse from the disk to the upper half plane. What are those maps? The first map from the upper half plane to the disk is I minus z over I plus z, is a Cayley transform of z. And g of z is the inverse of the Cayley transform. So this is a biholomorphic thing. And therefore, if you have any automorphism of the disk, phi from D to D, we have a map F, which is a biholomorphism from H to D. We have a map F, which is a biholomorphism from H to D. And therefore, there is a natural way that you get a biholomorphism from H to H. Namely, what do you do? If you're given this phi, I already have these F's and these F's here. Okay. And then what is the map that I take from this edge to this edge? The map is going to be from H. First you go from H to D, then you go from D to D by phi, and then you go from D to H by F inverse. Okay, so F inverse composed with phi composed with F is from H to H, and this is an automorphism of H because each of these maps are biholomorphic and they're automorphisms. I mean, they're not automorphism. This F is biholomorphic, this phi is a automorphism, and therefore this composition is going to be a biholomorphic automorphism of H. Okay, and therefore the map gamma from aught D to aught H, automorphisms of D to automorphisms of H, which is gamma of phi. Phi is an automorphism of D, and gamma of phi is should be an automorphism of H. What will you do? You just conjugate by, so this is called conjugating by F. Okay, gamma of phi is this, and obviously gamma of phi 1 composed with phi 2 is gamma phi 1 composed with gamma phi 2, and therefore gamma is an isomorphism of groups. Okay, what is the inverse? You can write down what the inverse of gamma is. So as you can see, topology is not the only place where you spend your time chasing diagrams. Okay, and there's a name that has been given to this going from phi to this map from H to H. What is that name? What am I just doing? Going from that phi downstairs from D to D to the map from H to H. Have you done this kind of thing when you were doing your diagram chasing in the topology class? Have you done something like this in the topology class?
Are you talking about universal property?
Some universal, something related to universal properties, but I mean, there was this word pullback or something like that used, pullback, push forward, that kind of thing. Okay, was it used there or not? I'm not sure.
No, sir.
Okay, hasn't been used. Anyway, it doesn't matter. Okay, so the point is that you will understand that there is this very natural way of going from an automorphism downstairs, that is downstairs here, to an automorphism upstairs. Okay, and this is called, this business is called conjugating by the biholomorphic function f. So there's a conjugation going on. What is conjugation? X inverse yx, that is a conjugation. F inverse phi f. Okay, and there is some very abstract thing that is going on here. That abstract thing can be thought of as, you know, this can be thought of in categorical terms, but as usual, you know, one must first think of this as a conjugation and then understand it as in terms of categories. So anyway, this is a isomorphism of groups. And what is the inverse of the automorphism? What is gamma inverse from aught H to aught G, aught D? Okay, so you should be able to write it down now. Okay. So what is the time? 5:30. What is SL2R? Now suddenly it looks as if I'm changing whatever I'm talking about. Just hold on a bit. The special linear group over real numbers are 2 by 2 matrices whose entries are real numbers, whose determinant is 1. Okay, so SL2R are these things. If M is in SL2R, M is equal to ABCD, these are real numbers now. Define Fm of Z to be AZ plus B over CZ plus D. So we had talked about these Mobius transformations. This is a Mobius transformation with the condition that all the entries are real. Now, I think somewhere I had said something about all the entries being real. I forget now. But I think when I was talking about this, I had said something happens to these Mobius transformations when all the entries are real. Does any of you remember whether I had said this or not? I have forgotten myself, but I will have to check in the notes. So this will be an exercise to you, that go back to the notes when I'm talking about Mobius transformations. And did I make some statement about what happens to the Mobius transformations when all the entries, all the ABCDs are real? So this fact that F, M1, M2, this is multiplication of matrices. This is composition of Mobius transformations. Okay, this statement I had made earlier, I'm sure. Okay, so M going to Fm is a homomorphism between SL2R, okay, and matrices of this kind, which are special cases of Mobius transformations. Okay. If Z is in the upper half plane and imaginary part of Z is greater than 0, so you can write down the imaginary part of Fm of Z. So I have to multiply it by Cz plus D the whole bar. So I multiply Az plus B into Cz plus D the whole bar, and I expand that out and I look at the imaginary part. Okay. So imaginary part of Fm of Z, please do this calculation, is AD minus BC imaginary part of Z over Cz plus D squared. Please do this. This is an exercise. AD minus BC is 1. So it's imaginary part of Z over Cz plus D squared. And therefore, if Z is such that imaginary part of Z is greater than 0, then the imaginary part of Fm of Z is also greater than 0. This means that Fm maps H to H. Okay, and you also know that Fm inverse is equal to Fm inverse. Okay, and therefore this is an automorphism of H. Thus, for each M, the entries are all real. Fm is an automorphism of H. Given a Z in H, I can find an M. So is that imaginary part of, why have I written M2? This is imaginary part of F of M1. So fix your Z. I can find an M1 of this kind. So that imaginary part of Fm1, that should not be a 2, that should be a 1, of Z is equal to 1. Okay, what do you choose C to be? You choose C to be this number and it works. Plug it into this formula. Okay, A and D are equal to 0 and BC is equal to 1. Okay, so it's of that kind, and this is imaginary part of Z over D is equal to 0, Cz squared, and I'm choosing C to be this. So imaginary part of Fm1, this is not 2, this should be M1, is equal to 1. Given Z with imaginary part of Z equal to 1. So if imaginary part of Z is equal to 1, that means it's on that horizontal line, imaginary part Y equal to 1. So it has some X component, and therefore I can translate it by a real number so that the real part of that is 0. So remember what does this 1v01 do? This acting on Z is Az plus B over Cz plus D. D is 1, C is 0. So it is Az plus B. A is 1. So M2 of Z is equal to Z plus B. That means you're translating by B. B is a real number. So the imaginary part does not change. And the real part gets translated by B. Okay? So I can find some B so that the real part of Fm2 of Z, which is real part of Z plus B, is 0. And therefore, by doing a combination of these two, you can find an M such that Fm of Z is equal to I. What does this mean? This means that every Z in H can be mapped to I by a M in SL2R. Okay? And remember, SL2Rs are automorphisms of the upper half plane. Every SL2R is an automorphism of the upper half plane. What we want to show is that they are all, essentially. So every Z in H can be mapped to I, and given Z1 and Z2 in H, there exists an M such that FZ1, FMZ1 is equal to Z2. That means the group of these M's, SL2Rs, okay, act transitively on the upper half plane. Have I written that down? Yeah, I have written it down. Where is this now? The group acts transitively, SL2R. This acts transitively on H. Okay, why? Because every element can be mapped to I, and therefore you take a composition of two elements. You take Z1 to I and take Z2 to I, and then take this times that inverse will map Z1 to Z2. Okay? The same argument again. So SL2R acts transitively on H. If theta is real, look at this particular element in SL2R. Okay? A, B, C, D. It has determinant 1, and this is in SL2R. This is an automorphism of H. Okay? This is an automorphism of the upper half plane. Now, if f from H to D is f of z equal to I minus z over I plus z, then f composed with, this is an exercise which you should do, f composed with this m theta, automorphism corresponding to m theta. So the exercise is f composed with the automorphism corresponding to this element in SL2R, is you take f acting on z and rotate it by e raised to 2 pi I theta. Okay? The image, remember, is in the disk. So this is an exercise which you should sit down and do. Okay, you know I'm telling you what fz is. I'm telling you what m theta is. Fm theta is az plus b over cz plus d. A, B, C, D are cos theta minus sin theta, cos theta. Okay? So this is another exercise which you can do quite easily. And therefore, f composed with fm theta composed with f inverse is rotation by the angle minus 2 theta in the disk. What is the final theorem? If you have an automorphism, then phi is of the form fm for some m in SL2R. Phi is an automorphism. Suppose phi beta is equal to I. Let n be the map which is such that fn of I is equal to beta, and therefore G composed with fn of I is fn of I is beta, phi of beta is I, so G maps I to I. Okay, and therefore f composed with G composed with f inverse, okay, is an automorphism of D, okay, which fixes the origin, because f inverse of 0 is I, G of I is I, and f of I is 0. Okay, so this is an automorphism of D that fixes the origin. Therefore, there exists a theta such that f composed with G composed with f inverse is multiplication by this. Okay, and therefore G is equal to this, and therefore phi is equal to this. So what am I trying to tell you? This proves that every automorphism is of the form that we are given, is of the form Fn for some n. Okay, so we found out the automorphism group of the upper half plane. Okay, now there's one slight problem here. Can I say that the automorphism group is equal to SL2R? Okay, But you see, you can go back to the definition. I'll repeat this next time. You can go back to the definition of Fm of Z, Az plus B over Cz plus D. Notice that Fm of Z is equal to F of minus M acting on Z. Because when you multiply the matrix ABCD by the sign -1, you get minus AZ minus B minus over minus CZ minus D, which is AZ plus B over CZ plus D. So F sub capital M is equal to F sub capital minus M or minus capital M. So whether you're looking at M ABCD or minus M, which is minus A minus B minus C minus D, the automorphism that you get is the same. Okay, so when I come down to this, okay, Fm is F minus M. So somehow I can't say that the automorphism group is equal to SL2R. Okay, the automorphism group, the isomorphism between automorphism group is not an isomorphism to SL2R, but it is an isomorphism to SL2R with the plus and minus signs identified. That means it's modulo plus or minus identity. So SL2R modulo plus minus identity. Plus minus identity is a normal subgroup. Yes, so I can take this quotient. So SL2R modulo the normal subgroup plus minus identity is called, the name that is given to it is called PSL2R, projective or whatever, PSL2R. So the theorem is that the automorphism groups of H is equal to, is isomorphic to, yeah, so I mean I should not say equal to, I should say is isomorphic to PSL2R. Okay, and we have essentially proved this. Now this is the beginning of some very interesting developments in mathematics. Okay, and these developments have been explained in Stein and Shakarchi, chapter 8. There are these exercises, so he calls them exercises and calls them problems. Okay, the exercises here are extremely interesting. The problems here are also very interesting. Okay, they have to do with hyperbolic distance, conformal. How do you map conformally to triangles, or how do you map conformally to polygons? There's something called the Poincare metric. The automorphisms preserve the hyperbolic distance, and then there are a huge number of ideas that are associated to this, and the outlines of these ideas are given in these set of exercises. Okay, so of course I would not expect you to do these exercises here and now, but again, these are one of the things that eventually over the next 6 months you should attempt to do. Okay, do it within the next year, 2022. Try to understand what these exercises are, and let me assure you, you will be, if you do these exercises, you will be very happily rewarded. Okay, so please at least look at these exercises and be aware that there are connections in many branches of mathematics connected to what we are talking about right now. Okay, so I should stop here. I've gone over time again by 4 minutes or something. So I'll repeat that last bit again next time. Okay, because it's always difficult. Any questions?